Good morning, everyone. Uh, we are excited to present our projects on timetable generation for IIT Patna, done under the guidance of Dr. Arijit Mondal. I am Udit Naran, and my team members are Ansu Kumari and Anu Kumari. In this project, we explored and implemented different algorithm approaches to solve the real-world problem of generating an optimal and conflict-free academic timetables. So this is the table of content we will cover in this slide. Introduction, problem statement, assumption made, optimization criteria, methodology, comparative results, and conclusions. So in introduction, we have to generate the timetable schedule. Like we have given the limited resources such as rooms, faculty, the student, uh, and the goal is to automatically generate a conflict-free optimized timetable using intelligent algorithm. So, in problem statement, scheduling a semester timetable is far from simple. At IIT Patna, a student enroll in various subjects, some core, some elective, and each subject may have lectures, tutorials, and practicals. So, on top of that, we have limited rooms and a fixed pool of faculty, many of whom teach multiple subjects. So the challenge is how can we assign all classes in a way that avoids conflict with follows constant like lunch breaks, lecture durations, and practical formats, while also optimizing the student experience. So in assumption made, to keep the problem manageable and well defined, we made a few clear assumptions. First, all schedules are conflict free, means no student, faculty, or room will be double booked. Second, all classes occur between 8 a.m. and 6 p.m. with a 1 hour lunch break at 1 p.m. and session follow valid lectures or lab formats. And finally, we assume that the input data from the academic sections, student, faculty, rooms, and subjects is complete and accurate and provided in CSV format. Beyond just avoiding conflicts, we aim to make the timetable as a student and faculty friendly as possible. So we focused on five main optimization goals. First one is minimizing lecture gaps between classes, okay, and reducing room switching for the students. Just like in lecture hall 3, after completing one lecture, the student don't need to go the another lecture hall. Uh, Next class will be on the same lecture hall. So by this way, we can save time. And also, next point is avoiding 8 a.m. and 5 p.m. classes. Early and late classes will be avoided. Ensuring a balanced lecture load across the week. So, lecture will be designed in such a way that uh, it can't be hectic just like for one day. It will be balanced between the days. So if lab is someday, then theory classes will be reduced, and if theory classes will be more, then lab classes will don't follow on this day. And making sure rooms and faculty are used efficiently. They form the basis of our post-function and evaluation matrix. So next part will be uh, discussed by my uh, teammate.
Hello everyone, I am Anshu Kumari from MTech AI. As we already discussed what is our problem statement, now let's discuss what methodology we have used in our project. We have used three types of algorithm. First one is CSP. We use ZT solver to solve the CSP problem. We encoded our problem in CSP and find ZT will able to find the conflict free solution for this CSP problem. The second one we have used it greedy heuristic approach, which is quick and basic and will find the first fifth session for every classes. The third one we have used is simulated annealing, which is a meta-heuristic algorithm, and it improves the random solution using probabilistic swaps. Now if talking about the input data, we have used 4 CSV files named student, subject, faculty and room. In student CSV we have a list of all the students and their corresponding subjects in which they are enrolled. Second one we have subjects CSV, in which we have list of subject along with their lecture sessions, tutorial sessions and practical session. After that we have faculty CSV, in which we have list of all the faculty along with their corresponding subjects. And last we have room CSV, in which we have list of rooms and labs with their corresponding capacity available. Now let's discuss our first approach, in which we model our problem in a CSV, that is constraint satisfiability problem, in which we declare some variables along with their domains, and we define some of the constraint, and Z3 will able to follow that constraint and find if feasible solution is possible for that problem or not. The CSV model this timetable as a set of variables with constraints and solve using backtracking approach. Now let's check what are the constraints available here for our problem. There should be room available and with the capacity available. For example, if a subject has 100 students, the room capacity will be greater or equal to 100. Now it also check for the faculty and student conflict. If a student is enrolled in two subjects, that two subjects should be on different times. Lab sessions should be scheduled consecutively. For example, if a particular subject have lab of 3 hours, that 3 hours should be in consecutive manner. Now if talking about theory subject, that we cannot have more than 2 hours of session for the theory subject. Apart from this hard constraint, we have some soft constraint also, which is not listed here, but it can be like there should be minimum gaps between the classes of for a particular student. Also the it is better to have classes after 9 a.m or before 5 p.m. Here CSP uses domain filtering and constraint propagation to reduce the search space. CSP guarantees the conflict-free solution if a solution exists. Now we have discussed about CSP. Let's discuss what are the limitation of the CSP problem. So CSP problem will be slow for the large input, but it gives accurate data. It requires precision modeling of all the constraints. However, it is very computationally expensive and scales poorly for large input size. So we will discuss a better approach than this CSP problem. So next approach we have used is greedy heuristic method. Here the greedy heuristic method is a fast and intuitive method which is able to make the timetable by step process, and heuristic method will look for the local optimal choice at that stage. Here we prioritize the subject based on the total number of session, lecture plus tutorial plus practicals we have for that subject, along with the student enrolled in that subject. After that, we have assigned session gridly to earliest possible slots, rooms, and faculty available for that subject. It is faster and scalable approach, but does not always yield optimal solution. It is good for the real-time application, but there are also some limitations for the greedy heuristic method also, as it only gives locally optimal solution. It does not look for globally optimal solution. And for our problem, that is large data set with many students, subjects and rooms, greedy strategies may degrade the performance or quality. So our next approach will be simulated annealing, which is discussed by my friend Anu Kumari, and she will be moving forward from here. Thank you.
Hello, my name is Anu Kumari. I am from MTech AI. In this slide, I will discuss about the Meta-Heuristic algorithm, which is based on the simulated annealing we have implemented in this approach. Earlier, we have seen the two-method algorithm, which is Z3 and heuristic based approach. In this slide, we will discuss simulated annealing, which is mainly we have start with an initial valid timetable, then improve it through the iterative changes. Randomly, we swap session and evaluate quality based on and define the cost function such as gaps, room changes, etc. We have accepted the worst solution early on to the escape the local minima and gradually becomes more selective, balance exploration and exploitation using a temperature parameter, which yields high quality solution, which is better trade-off between the performance and time. We have some limitation of this meta-heuristic algorithm. First is simulated annealing is probabilistic and may settle on a local optimum rather than the global best. And the second is the compared to the heuristic, meta-heuristic often require more time to converge to a satisfactory solution. In the next slide, we have compared the result among the three algorithms, which is CSP based Z3 and heuristic based greedy algorithm, and third meta heuristic, which is simulated annealing. This is the criteria we are including for our comparison. First is conflict free timetable, gap between lectures and room switching for the student, early and late hours classes, execution time and scalability and implementation complexity. This is the greedy algorithm, which have some advantages and disadvantages of their execution criteria based, and this is simulated annealing, which have mostly conflict free, which minimize the gap between the lectures, and the room switching is reduced, and it also reduces the early and late classes, and execution time is moderate and scalability is moderate also, and implementation complexity is moderate. But in Z3 we granted the conflict free timetable, and also it minimized the gap between the lecture, and room switching for a student is significantly reduced, and it is highly avoided early and late classes, and execution time is also slow, and scalability is limited for the solver, and complexity is formal. So based on this, we have the Z3 based approach has a better result as compared to the greedy algorithm and simulated annealing, I think. Based on this, we have concluded that we have three applied approaches, CSP, heuristic and meta-heuristic, successfully generate the valid institute-wide timetable without student or faculty conflicts. So CSP is accurate but slow, and heuristic are fast but may reduce the quality, and simulated annealing balance the speed and the quality. We have the three results. Based on the we have performed our algorithm, and we have seen this result. Timetable were evaluated based on student gaps, room switches and early late classes and conflict avoidance, and we have some future scope. In the first, we have used CUI inference, real-time conflict detection, adaptive optimization. It may be used for the future also, and this for future improvements we could include the dynamic room allocation, real-time updates, and integrating students' preferences or elective conflicts. And thank you.